All right. Hi, everyone. Good morning. Thanks for coming here at this early hour, especially after last night. Welcome to our talk on multi-threaded Node.js applications. Is it worth it?
So yeah, who are we? I'm Thomas Hunter. You might remember me from karaoke last night.
I'm Bryan English, and maybe you do remember me, maybe you don't. Here are our handles on every internet website. Yeah?
That's right, except for Blue Sky.
Except for Blue Sky.
So yeah, we wrote a book. It's called Multithreaded JavaScript. Have a copy. We'll figure out how to give it out later today. And we wrote it in 2021. And yeah, it's the Goose book.
The Goose book. So yeah, we work for Datadog. We work on Datadog APM. So for all your fun observability needs, please come to us. And also we're hiring, as always. So if you're interested in any of this or any observability problems, that kind of stuff, we're always hiring. All right, jumping right into it with some definitions. Concurrency versus parallelism. Fun misconceptions around this all the time, so defining them real quick. Concurrency, tasks are running in overlapping time. Parallelism, tasks are running in exactly the same time. The diagrams kind of make it a little clearer here. But first of all, quick show of hands. There we go. One person got that one. Yes, two, there we go. Yeah, so if you believe that the JavaScript event loop is more of a concurrency model, raise your hand. If you believe it's more of a parallelism model, raise your hand. Perfect, all right, we got a good crowd. Yes, obviously concurrency for most of the time, but of course we have threads available, so parallelism is a thing too. All right, so now I want to talk about 5 things that, these are things that we've heard people say fairly recently in our work. There's a lot of misconceptions, so let's dive into them. First one, JavaScript is single-threaded. I mean, of course, this is a lie. We're here, we're at this talk, we wrote the book, it's obviously a lie. But no, there's obviously a long history of JavaScript being single-threaded. We obviously can't create new threads using the built-in API itself. It relies on the host platform to do that. So it's very easy to fall into this sort of misconception trap. The next one, I need to scale to n processes if I have n cores. This one we see a lot of. You know, people check os.cpus or something like that and just assume that that will always be the right number for how much they should scale, either with processes or threads. The right answer here is obviously to measure, right? You're never going to know the right answer until you actually measure. Okay, line number 3, I need to give it 1 core or less. So often we see this in like Kubernetes deployments. People will give it something like half a core, like 500 millicores, something like that, thinking, okay, JavaScript is single-threaded, so surely this should be enough, right? As we'll get into in a later slide, this even out of the box with just 1 thread in Node, that's you're still not actually single-threaded. All right, line number 4, you can't do any multi-threaded programming in JavaScript. This one is really huge on Twitter. And again, we're here, like, what are we doing, right? All right, and the 5th lie, processes are the only way to get true parallelism in Node. Yeah, that may have been the case many years ago, but we've had threads for a while. We have threads in the browser now. We can use true parallelism today.
Great, thanks for that. Let's now go through some basics. So quick, fun little fact, your Hello World application in Node is technically multi-threaded. So here we have a command on a Unix-like system. It will show the number of threads used by a given process. And so here we just have a simple Hello World application with a long set timeout to keep it around. And so by default, we're seeing about 7 threads per program. So what does that include? Well, that includes V8, it's actually running your JavaScript, but there's also a garbage collector, and libuv itself has a thread pool. And so by default, under the hood, there's actually a bunch of threads being consumed by a program. So you might be wondering, okay, what's the difference between a worker thread and a child process? Well, when we wrote the book, spawning a new thread is a bit lighter. And so these numbers change a little bit with versions of Node, but at the time, we saw that by instantiating a new thread, it would consume about 6 megabytes of memory, whereas instantiating a new process would be about 32. So each one of these threads, they do end up having like their own event loop and a bunch of sort of globals that come with them. One thing to keep in mind is that you cannot share an object reference across either approach, either with worker threads or child processes. You can't
Yet.
But yeah, otherwise you can't, mutate the same object at the same time. You can't really share processes or memory between processes. You could probably hack something together in C, but otherwise memory can't be shared when dealing with processes. Another thing to keep in mind is that in either case, the operating system is sort of scheduling when work is being done, what's the order that stuff is executing. Even with the single-threaded application, at the end of the day, the operating system does make a lot of decisions. All right, so why would you use threads? Well, there's really sort of two conditions that would need to be met. So the first is that your application's performance would actually benefit from parallelism. It doesn't always, which again, sort of the emphasis on testing. And also your system has additional cores available. So if neither of these conditions are met, then you probably should not be using threads or sort of any of the things we're discussing today. So quick API overview. If you were at the multi-threaded workshop yesterday, this stuff should be familiar. Or if you've, of course, done your own research, this should look familiar. But otherwise, we're just going to quickly cover it here.
Or if you read the book.
That's right. Raise your hand if you read the book. For those at home, half the audience raised their hand. All right, so at our disposal, we have a message event handler, and we have a post message method available to us. And so these allow for bidirectional communication between a parent thread and a child thread. And these things end up forming, essentially you build like a hierarchical relationship between these threads. And so these messages, when you sort of send them between threads, they end up getting queued up in the event loop, and then the message handler fires off when the thread the event loop is available. And so we also have a shared array buffer, which is essentially an array buffer, except as you could probably guess, it could be a shared or otherwise referenced between multiple threads. And so this is just a bunch of memory that we're able to write to. And finally, we have atomics, which is a global singleton. It's an object with a bunch of methods hanging off of it. And there's basically two classes of methods available on it. One is that of data manipulation, and the other is used for coordination.
All right, so now let's talk about some of the patterns that we've seen folks use and that we've used ourselves when it comes to threads. So really, you can mostly categorize these patterns into three different groupings, right? The first one is just message passing. So this is when folks are building multi-thread applications relying solely on post message and on message. So basically just passing data back and forth between threads using these built-in primitives rather than anything else. The next obvious one is just relying solely on your shared memory. So having your shared array buffer and doing appropriate locking and stuff and using that for synchronization rather than post message. What we find a lot more folks doing, though, is using a combination of the two, and that's basically using post message and this sort of thing for synchronization, and then shared array buffers for the larger chunks of data, the inputs and outputs to your functionality. So just diving into each of those a little bit, obviously the message passing is your simplest pattern because it's just calling functions, handling events, stuff we've done in Node forever. So yeah, it's certainly the simplest to work with, handles most of the synchronization stuff for you behind the scenes, but it does come with some overhead, in particular serialization, and we'll get to that in a minute as well. So yeah, I mean, it is the least performant way to use multiple threads, but you do get the benefit of the simplicity. All right, so in the shared memory pattern, where you're relying mostly on shared array buffer and atomics, it's definitely the most difficult to use. If you were in the workshop yesterday, I bet that was the hardest chunk of the workshop. And so like you need to use low-level operations like the atomic, things that are on the atomics objects to actually do all your coordination. And of course, you do this sort of thing wrong, you can come with risk of data tearing or interleaving. I think this image is from Half-Life, right, Tom?
Right, Half-Life.
Right, it's Half-Life. So this is just an example of tearing happening in a video game because, of course, graphics processing is just multi-threaded programming from a different perspective, right? And it's a similar thing happening here. So yeah, I mean, using this approach, you end up with the most performance because you don't get the overhead that you get with post message, but you also have the most pitfalls. So yeah, again, the hybrid approach is what we see most of just because it finds that sweet spot of simple synchronization, but also better performance for dealing with the larger amounts of data. So yeah, it's a middle ground for performance and complexity.
Great, so now that we've looked at some patterns, we can sort of try to make things a little more concrete, a little more real world. So we'll look at some further use cases. So one use case we have is that of horizontal scaling. So in this case, you can imagine sort of a re-implementation of cluster, which is a way to run child processes as a form of scaling. And so with this pattern, imagine having the main thread being essentially like a sort of router that routes incoming requests into different workers to handle it. And then with this pattern, each thread ends up, handling the entirety of a request. And so each one of these request handlers, they're doing the same thing as each other. In the main router in this pattern, you could just do simply round robin or some sort of approach like that to distribute requests. And then using this pattern, you could actually implement it entirely using the message passing pattern. You wouldn't need to do any shared memory necessarily with this. We also have that of off-thread rendering. And so, again, sort of the diagram looks similar, but in this case, we would have the HTTP handler in a singular location. So you can imagine our best friend Fastify running there, sort of routing requests, request handler. However, instead of offloading all of the work to the different threads, in this case, you would only offload a chunk of work which happens to be CPU intensive. So in this case, maybe you're doing rendering of React templates, something like that. So that's the kind of stuff you can offload. And so for the book, we actually did this and built a simple application. We wrote the book a few years ago, so at the time we chose a mustache. So in this case, the worker threads do all the mustache rendering, and the main worker did everything else. So just a quick autocannon test suggests that by doing everything in a single thread, we were able to get 25,500 requests per second. However, upon offloading the rendering work to the worker threads, we got 40,500. And so just to sort of visualize what this looks like as far as taxing the event loop in the application itself, in this case we have a graph that shows over time the event loop delay. And so it's sort of the way this measurement works is we have a set interval, and every second it gets the current time with process HR time, then it does a set immediate, gets the time again, subtracts the difference, and then we graph it. So in this case, when we do the work on the main thread, we see that there's a latency of about 750,000 nanoseconds. However, when we offloaded the work to the worker threads, in that main thread, the latency got much lower to about, 300,000.
Cool. So then this next use case, divide and conquer, you'll notice these diagrams look very similar. It turns out there's a class of problems that are easier to solve using threads, and so that's what naturally lends itself to this. Sometimes we call these problems embarrassingly parallel because it's just so obvious that you'll get some benefit out of parallelism. And so for the book, one of the examples we came up with is just using Game of Life, Conway's Game of Life, which if you think about that, that's just a map of cells that have a state either alive or dead, and then the next state is dependent on the previous state of neighboring cells. And so this is just a whole bunch of calculations that needs to happen, so it makes sense to sort of divide and conquer this operation. And so we did do that for the book, and so there's a great example in the book that you can work through using shared array buffer and atomics. And so here it is running in the browser, and so this is the example running with just one thread, just the main thread. And there it is running with 6 threads. This is live in this browser that we're presenting with. Another interesting point about this is that we are using Firefox for this demonstration because it happens to show the biggest difference. And this just kind of goes to show you, you really need to test on the platform you're deploying to see whether these are all appropriate.
Great. Now let's look at some further considerations. The biggest one, of course, being performance. So one thing to keep in mind is that every single application and every single environment is going to be unique. So what that means is that you cannot possibly test your application on your MacBook Pro and then see that the performance has certain characteristics and then ship it to production and be confident. Instead, you must test your application in a real-world environment, if possible, same CPU, same allocations, etc. So we were working with a customer at one point, and we found that they had an application that would run completely fine in production. However, it would lock up in staging. And so after much research, it was discovered that in staging, they had only allocated 100 millicores, or 10% of a CPU for their application. However, in production, they had multiple cores allocated. And so for that reason, the two environments behaved quite differently.
That goes back to our lies from the beginning, right? Considering how many cores you need.
That's right.
All right, so like I said, a little bit more about serialization. Obviously, when you're dealing with raw data, which in some manner you're going to have to because you can't pass objects across today, you have to deal with serialization at some point. Either it's built into what you're doing because you're just using the memory directly, or you're using regular JavaScript objects and you're using something like structured clone, JSON stringify, or message pack. And all those things are slow. Serialization is slow. I mean, raise your hand if you've run into a performance problem due to serialization. Yeah, like everyone, right? It's just a thing that always happens, and it becomes more prevalent, or it can seem to be more prevalent when you're dealing with multi-threaded JavaScript. So for example, the library that we work on, it's called ddtrace, Datadog tracing. We can't just simply send data off to another thread for serialization, because fundamentally what we do is we gather data and we ship it off. We can't just do the serialization off thread, because in order to do that, we would have to serialize to get it onto that thread, deserialize it there, and then serialize it a third time, or second time. That's too much work. And if you try doing something like that, it's just going to slow everything down, right? So today, all of our state is on the main thread, but one of the things we've been looking at in the future is to have a separate thread for state storage that would also be where all our serialization would happen for data egress later on. So yeah, that's a pattern that we have seen, for example, customers do for other things, and it seems pretty useful.
Great. And another important concern is that of code complexity. So when it comes to threads, usually if they're doing the same thing, they're easier to think about. But if each thread is doing something special, it gets a little more hard to think about. Another issue is that of having too many locks. And so locks are a way to sort of coordinate between threads. And the more of those you have, the harder it does get to debug. Another current issue is that there's no built-in mutex available, which is it's like a low-level locking primitive used in multi-threaded applications. So instead, you have to sort of roll your own. And of course, since there's,
So far.
And since there's no shared objects today, that means a lot of the code you end up writing, it sort of looks like C. You're just writing C in JavaScript. There's also other sort of class of problems you can have, that of deadlocks or race conditions, and they're a lot harder to debug than your typical single-threaded application. So ultimately, this stuff may be worth it for a performance sake, but eventually get to the point where you do have to ask if you should really be building this application in JavaScript if performance is that high of a concern.
All right, so this is a fun bit. When we wrote the book, we had a bunch of folks reviewing it, some of them in the room. One of them was Shu, who works at Google on a number of things, including taking part in TC39 on things like threads. And so when he reviewed the book, This was his commentary. He said, frankly, my main takeaway after I finished the book was disappointment in the state of concurrency. Yes, he means parallelism. On the web platform. I'm working to rectify that, but it was a reminder of just how early days we are still. So of course, that was 3 years ago. And since then, Shu has actually been part of the Structs proposal, which maybe you've seen recently. So Structs gives us a whole bunch of interesting stuff. First of all, Structs themselves, which, long story short, it's basically a stable object, memory stable. So then we have shared structs. The shared structs are just a subset of those that can be transferred across threads. Fantastic. That takes away at least some of the problems that we've talked about today. There's now a built-in mutex object class, really, that gives us that out of the box, which makes a few other operations easier. And also shared array, which is just a special case of structs for arrays, basically. There's also the unsafe block, which is where all property access happens. It's a whole bunch of good stuff. I really highly recommend taking a look at the Structs proposal if you haven't already. And of course, this means we're going to have to do a second edition of the book, of course. And this is just this is directly from the Structs proposal itself. This just shows some of the stuff that can be done with it. In this case, it's showing a point object, so like X and Y coordinates that's shared across threads. The obvious joke there is Microsoft SharePoint. But yeah, this is using the new mutex. It's using the unsafe keyword and all this. This is directly from the proposal, so this, in my mind, is probably one of the best examples we have of like what code could start looking like in the future when it comes to multi-thread programming in Node and JavaScript.
Great, so that's the presentation. If you want to get a copy of it, you can scan that code on the left. It'll take you to these slides. If you're interested in the code samples, these are the samples that were taken from the book. So there's a whole repository of them, so you can experiment with it and even run your own benchmarks. And that's the one on the right. And as Brian mentioned, keep an eye out for a multi-threaded JavaScript 2nd edition, part 2, Electric Boogaloo. We'd have a big spreadsheet full of plans, but no promises on when it'll be out. All right, thanks everybody.
Both and never.